Stripping down science. The Naked Scientists.
Hello, it's Sunday, the 2nd of October. Welcome to The Naked Scientists. I'm Chris Smith, and also here with us this week are Dave Ansell. Hello, Dave.
Hello.
And also Dominic Ford. Hello, Dominic.
Hi, Chris.
Now, together, we're all taking on your science questions this week, including what makes leaves change colour in the autumn? Would swimming out of a submarine give you the bends when you got to the surface? And lots of debate on the forum about this one. Would a siphon work on an orbiting space station? Dominic.
Plus, the Messenger probe has discovered that Mercury may have had less of a hot and violent history than previously thought.
And talking about hot and violent, this week I'm going outside to start a fire for kitchen science, but I'm not using matches, a lighter, or even rubbing two sticks together.
So what is he doing? You can find out later. And if you'd like to get in touch with us here at The Naked Scientists, you can tweet at Naked Scientists. You can also write on our Facebook page, that's at thenakedscientists.com/Facebook, or drop us an email. Our email address, chris@thenakedscientists.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
The Naked Scientists with Chris Smith, with Dave Ansell and Dominic Ford. And straight into outer space this week, or at least to the solar system. Dominic.
The journal Science has published a special issue this week presenting the first 90 days of observations from the planet Mercury by the Messenger probe. Now, Mercury is quite an interesting planet because it's the densest planet in the solar system, and it has a strong magnetic field, which suggests it probably has quite a dense iron core. It's also interesting because it's a geologically dead planet that we don't think has seen much change in the last 3.5 billion years. So it gives us a nice window on what the early solar system may have been like. Now, in terms of data from the Messenger probe, it is very early days. This probe only arrived in orbit around Mercury 6 months ago in March. And so what we're seeing being published at the moment are really strands of observational evidence which will feed into models of Mercury's formation, but some of the interpretation of those results, I think, is going to come in the next few months rather than being there already.
How big is Mercury, Dominic? It's quite small, isn't it?
Mercury is smaller than the Earth. I think it's about a third of the radius of the Earth. And that's
very close
interesting.
to the Sun.
Very close to the Sun. And interesting it should have such a strong magnetic field, because that suggests its core is not that much smaller in comparison to the Earth's core. So it's probably got a very large core at a fraction of its volume, perhaps about 40%. Now, we've got the first measurement of the composition of the surface of Mercury from Messenger, and that's an interesting contrast from the other terrestrial planets. In fact, the composition we're seeing is closer to what you'd expect for a comet. Now, that's perhaps suggestive that Mercury's surface is littered with dust from comets, and this is actually cometary material originally that we're seeing. Another interesting point is that Mercury has quite a high concentration of potassium on its surface. Now, potassium is volatile, and it boils at a relatively low temperature. And this is where we come to the point that Mercury probably hasn't had a very hot and violent history, because otherwise that potassium wouldn't still be there. It would have boiled off in Mercury's past evolution. We also have measurements of Mercury's magnetic field, and the interesting point here, the shape of the field is similar to the shape of the Earth's magnetic field, but it's displaced toward the North Pole. So if you imagine Mercury's surface as being spherical, the magnetic field is a sphere but displaced to one side, which is rather odd, and I think we don't know what's causing that.
Would the mechanism by which it makes its magnetic field be very similar to what we have on Earth?
That's a really interesting question, and I think we don't really know how Mercury generates its magnetic field. This is definitely a clue, and I think watch for journals in the next 6 months, and we'll probably see some interesting papers coming out on that.
The conditions that the probe is experiencing around Mercury, will they be much harsher than anything that we've really had to do before because of its proximity to the Sun? The incident radiation and so on must be quite high there, isn't it?
That is a very interesting point, because the probe is entering into Mercury's magnetic field, and what it's seen is bursts of electrons from the solar wind. That is completely different from what you would see in, say, orbit around the Earth. The Earth has what are called Van Allen belts, where radiation becomes trapped in orbit around the Earth, and you see a very steady flux of those electrons because they're trapped for long periods in orbit around the Earth. These particles come in bursts because we're much more exposed to the gustiness of a solar wind, because Mercury's magnetic field is that bit weaker than the Earth, but it can't trap these particles in the long term. So you're really exposed to what space weather is doing this week, rather than averaged over a long term.
What about the surface of Mercury? Have they actually got anything on that?
This is perhaps the most fascinating point of all. They're spotted pot marks on the surface, where there seems to be some kind of subsidence. And we don't know what's causing these, they weren't predicted, but the best model we have is that you have newly formed craters which are digging up previously buried material. The sun's rays are heating that material, and if you have volatile materials, then those volatile materials will evaporate for the first time, they will leave voids, and you'll get collapses to form these pot marks. So that's more evidence of volatiles on Mercury, so not a hot and violent history.
Now, on a completely different subject, plastics may soon be able to be designed to a specific specification, so you make designer plastics. Now, plastics are used all over the modern world, from toothbrushes to fighter jets, because they have a wide range of useful physical properties. This is partly because there's lots of different plastics with different chemistries. But two plastics with the same chemistry but different structures can have very different properties. Plastics are polymers, they're made up of repeating chains, and petrol, wax and polythene are all just different lengths of the same type of hydrocarbon chain. But it's not just that, also chains don't have to be straight. They can either be straight or branched. A number of branches and the length of the branches can radically change the properties of a polymer. This is a huge advantage, but there's also a problem, because there's so many different types of polymers out there, it's really difficult to find them. And up until now, people have been doing this just by trial and error.
When you first started saying that, I thought you were going to use the word kinky, like kinked chains, and I thought, no, that's probably actually an association with rubber and other kinds of polymers, probably a bad picture to have in your mind. But how are they doing this?
Well, I mean, up until now, it's just been trial and error, which is great for polymers which we've spent 50 years studying. But as new biologically derived polymers are turning up, there's a huge problem, because we want to kind of get to the same state as we are with polythene, but with these new polymers. Now, Daniel Reed and colleagues from Leeds and Durham universities have been trying to make this process a lot more efficient. They've developed a computer model which will take the conditions for making polythene, because start on the plastic you understand, in the reaction chamber and predict the degree of branching. Then they feed this data into a second computer model which will take the shape of your polymer and predict the physical properties by predicting how the polymers will move relative to each other and how the ends can move past one another. And they've done this, and they've worked it all out for polythene because they understand it, and it works really, really well. This means they can already predict the conditions you need to produce a polythene of a specific set of properties, but in the future you could also use it if you wanted to recycle polythene. You're mixing different polythenes, and in a blend you want to get a certain properties. That would be very useful.
Well, that's neat, because that's a really big problem, isn't it, when people don't know whether or not they can use a certain combination of materials. Because, I mean, taking an aeroplane, I know it's not a polymer, but taking an aeroplane as an example, a man who recycles aeroplanes told me the other day, you can't recycle the materials in an aeroplane because the manufacturers don't know what the composition is, and they can't guarantee the material's behaviour unless you start with pure materials. So the aeroplane ends up turning into beer cans. You can't turn it back into a new plane again, which is a terrible way. So this, for the polythene equivalent, sounds really promising.
So maybe not to put into aerospace, but certainly in a lot more situations, because you know what's going to happen if you mix this bucket of stuff with that bucket of stuff. And also, it would be involved in finding a few experimentally derived numbers to feed into their models to use a completely different kind of system of polymers. So with all the biopolymers, they should be able to just feed into more numbers and do the same thing with those.
Like all these things, you think, that's not actually that difficult. So why has it taken so long to do it? What's held them back? Why have we only just seen this happen now?
I think you've got to understand how polymers move past each other. It's actually incredibly complicated, because if it's actually a huge mess of tangled, in some places they crystallise and they can move past each other by kind of wriggling like snakes. So you've got to understand that, and then you've got to build it, and then you've got to have the computers available which are powerful enough to do it, and then you've got to combine the two, and so it just takes a lot of effort and it takes a while.
Thank you, Dave. We seem to see a lot of stories recently where people are really bringing computer power to the fore and doing this kind of modelling. It's really accelerating research in quite an interesting way. An analysis of over 500 million tweets worldwide has confirmed that, regardless of country or culture, we're all in a better mood in the morning. Scientists at Cornell University have analysed the messages posted on the Twitter micro-blogging site by 2.4 million people from 84 different countries. One of the authors, Michael Macy, is with us to explain why they did this and what they found. So what were you aiming to find out, Michael?
We were looking to see how people's moods change over the course of the day, over the days of the week, and over the seasons of the year using Twitter, which allows us to monitor people's affective expressions in real time at a global scale across diverse cultures, which is something that scientists have not been able to do in the past.
Talk us through the method. You presumably didn't read 500 million tweets individually.
That's right. It's all processed using computers. In fact, you wouldn't want to try this on your desktop computer. We used Cornell Center for Advanced Computing, a large cluster of powerful supercomputers. And what we did is to basically, for each user's a given hour in a given day, like let's say Tuesdays at 9 a.m. to 10 a.m., we would take all the messages that they wrote during that time period on that particular day and throw them together kind of as a bag of words, if you will. And then the computer sorts through that bag, and it identifies all the words that are positive words like awesome, fantastic, incredible, hilarious, and also finds all the negative words like unhappy, depressed, embarrassed, anxious, afraid, and so on.
How does it handle sarcasm? So if I said, brilliant, just got fired, how would it cope with that?
It would get it wrong. And one of the advantages of having such a large number of messages is that the errors will tend to cancel out at very large numbers. So you get a little noise with people using sarcasm or, for example, saying good morning in the morning just as a ritual, but not as an expression that they're actually feeling good. But when you have this large a set of observations, in this case over 500 million messages, then the errors tend to cancel out. And the reason that we know we're seeing the errors cancel out is that we get a very robust pattern. It holds up. We see the same thing each day of the week. We see the same thing across very diverse cultures.
And since you say you saw these patterns, what patterns did you see? What did the analysis reveal?
Well, basically, we found that people are happiest in the morning, and then it's kind of all downhill from there. But then in the evening, there's a rebound in positive feeling, right on up through bedtime, with a second peak in the late evening. And we see this pattern every day of the week. So it's not just work that's doing it. It would certainly fit with what we think about work as something that makes us tired, it gets us stressed out, frustration of commuting, and so on. But we actually see the same pattern on the weekend. So these two peaks with a trough in the late afternoon seems to be something that's kind of built into human body rhythms, and it's independent of the day of the week or whether you're at work or not. On the other hand, people are also happier on the weekend, which does suggest that there's something going on with work. But the peak on the weekend is a little bit later. It's about an hour and a half to 2 hours later than it is on the weekday, which suggests that people are sleeping in. Whereas on the workday, they're getting woken up by an alarm clock. On the weekend, they're perhaps sleeping until their body's ready to wake up. And so it could be that the elevated mood on the weekend is actually a response to having sleep that is not interrupted artificially by an alarm clock.
It also tells me that the people you analysed in your study obviously didn't have kids, because they wouldn't have been afforded the luxury of a 2-hour lie-in. What about one other quite important thing, which is, and I guess you may have been able to test this with this sort of data set, seasonal affective disorder. The whole idea that as we shift through the seasons, people at very high latitudes are being exposed not just to an absolute reduction in day length, but to a changing day length. Do you see this mirrored in the moods indicated by your analysis?
Yes, we do, but it's not the absolute amount of daylight that you're getting, or how long the day is in absolute terms. It is the change from what you're used to. So what's happening is that as the days are getting longer, moods are improving, and as the days are getting shorter, then moods are not so good. And it's the change in the day length, not the absolute length of the day, that seems to be associated with changes in mood.
So what's the bottom line with this study? Why is this important? What have you flushed out from doing this that we didn't know previously from other sociological experiments on small groups?
Because we had such a large set of observations from all over the world, we're able to have more confidence that we're we're nailing down when in fact it is that people are in the best mood. And then we also had some surprises in the results, finding the same pattern on the weekend and finding the same pattern across very diverse cultures was something of a surprise. You know, you would think a country that's collectivist, for example, or has a different religion from the U.S. or from the U.K. or Australia, you would think that perhaps they would have different patterns of when people are in a good or bad mood. But in fact, we found very similar patterns all across the globe, whether it's India or Africa or the UK or the US, Australia, very similar patterns.
And what are, to finish, the implications of that?
Well, one of the things we'll want to do is to break down a little bit in more detail the different groups within this large population in different ways. So, for example, one of the things that we looked at that we might want to investigate further are different chronotypes. A chronotype is a person who's active at a particular time of day, such as a night owl or a morning person. And another one of the surprises was that we found out that night owls are different from everybody else in a sort of peculiar way. Everybody else has the second peak when their moods rebound in the evening, and you would think, well, certainly night owls will too, but in fact we found the opposite. The night owls just have that peak in the morning like everybody else, but they don't have that rebound in the evening. They're basically the group that's the least happy in the evening, and yet they're the group that's the most active. So that was a bit of a surprise, and we'll pursue in more detail those kinds of breakdowns of who in the population is reacting in what way.
All right, we must leave it there. Thank you, Michael. That was Professor Michael Macey from Cornell University, and he published that work this week in the journal Science. Now, talking about using computers, this is another one. Actually, there's a group of researchers at the University of Michigan this week, a group led by Zishan Saeed, and they've got a very nice paper. It's in the journal Science Translational Medicine, and it looks at very old technology, the ECG. We've had ECGs around for decades, actually. These are the tracings that you make on the heart, and what you're doing is recording small electrical currents from the skin that are produced when the heart muscle itself depolarizes or beats. And one of the things that we do with an ECG is to look at the shape of the waveform, the electrical pattern, because certain heart conditions can produce changes in that pattern which mean something to doctors. But also lurking inside those signals could be some other really useful information that we previously have overlooked. And what this group did was to feed in 4,500 patients worth of long-term ECG traces, and they then married up what those tracings look like with the clinical picture. In other words, how those patients who produced those ECGs got on and what their problem was and what their long-term outcome was. And they were asking the computer to try to match up any corresponding changes in the ECG that tended to go with a certain clinical outcome. Because what they were looking to do was to build what they called 3 independent extra biomarkers. In other words, signs that if someone has those things, they would be at a higher or lower risk of having another heart problem. And I should mention these are all patients who had a previous heart attack.
So there could be some data sort of hidden in a little twiddle at the top of the ECG, which if you looked at it with your eyes, it'd be completely overwhelmed by the major part of the trace.
Yes, and the other point that they make is they're looking at long-term ECGs. So if you just take a snapshot in time, 10 beats of a person's heart, which is what a machine might do, you might miss a longer-term thing which crops up less commonly but may or may not be linked to something significant for that person. So having fed in these 4,500 ECG tracings and asked the computer to marry up the long-term picture with the clinical picture, they arrived at 3 independent, what they call biomarkers. They haven't got the most exciting names, but they've got one which they call MV, or morphological variability, and this is how the shape of that person's ECG or electrical tracing changes with time. So does it remain stable, or is there a gentle change? Because that can be prognostic. They also have something called a symbolic mismatch, the SM, and what this does is it compares the patient's ECG trace with a whole range of general population members with the same sort of clinical picture as that person, which in other words asks, is this person's ECG grossly different, or is it very, very similar to the average? And that can be useful. And they've also got one called the heart rate motif, the HRM, and this looks at the frequency with which risky rhythms turn up in that particular patient. And they're saying that they can actually use this data to make very, very useful predictions about someone's risk, because there will be people who have certain changes in their ECG which will put them into a higher or lower risk bracket, and by putting people into those particular brackets, you know who the ones are that you need to focus on, follow up sooner, give more aggressive drug therapy to. The lower risk patients, you could spare them those relatively unpleasant investigations and extra drug therapy they don't need, and therefore minimise their side effects. And I think the exciting thing, as they point out in their paper, these biomarkers can be extracted from data that are already routinely captured from patients with acute coronary syndrome, in other words, having a heart attack, and they will allow for more accurate risk stratification and potentially better patient treatment. In other words, it's a way of getting extra information from ECG data that we already capture on most people.
Essentially for free.
And exactly, for free. Now, with a look at what else has been making scientific headlines for us lately, here's Mira Sinthalingam with this week's Naked Scientist Newsflash.
China has launched its first space station, set to orbit 220 miles above the Earth. The unmanned Tiangong-1 space laboratory, meaning heavenly place, was launched from the Gobi Desert on the 29th of September, carried up by the rocket Long March, and will remain in orbit for 2 years. Anu Ojar from the National Space Centre in Leicester comments.
In a couple of months' time, in November, there'll be the mission called Shenzhou 8, practicing rendezvousing and then docking with Tiangong-1. Now, that's going to be unmanned, and the plan is for that to stay up there for 12 days. What will then follow over the next year are 2 more missions, one of which will be manned. The declared plan is to have Tiangong-1 altogether on orbit for about 2 years, with Tiangong-2 following as a successor in 2014.
High-resolution images of the Dead Sea Scrolls are now available online. 5 major scrolls of these ancient manuscripts, originally written on parchment and papyrus, have now been digitised by Google in collaboration with the Israel Museum, enabling billions of people to access these biblical texts in their original form. As Geza Vermes, Emeritus Professor of Jewish Studies at the University of Oxford, explains.
One of the most important contributions is that people can see the actual scrolls as they are, the color of the leather, shape and darkness and spots of ink on the manuscript, so that they can actually come as close to the documents as those who can hold them in their hands.
Carbon dioxide emissions could soon be converted back into fuel, reducing levels of this greenhouse gas released into our atmosphere. Using a process dubbed artificial photosynthesis, Rich Maisel and colleagues at the company Dioxide Materials have used solar energy to convert carbon dioxide into carbon monoxide and water, which in turn is combined with hydrogen to produce synthetic gas, which is now used by many oil companies to produce fuel.
It's a viable route in the long term to make the fuel for your car or your truck or your airplane that doesn't compete with the food supply, and it's completely renewable and recyclable. So it changes CO2 from something we dump or have to bury into something that we recycle and reuse, and it's a renewable resource.
Glowing bacteria could soon be used to encode secret messages. Working with E. coli and fluorescent proteins, David Waltz from Tufts University used combinations of bacteria to encrypt messages onto sheets of paper made of nitrocellulose. Potential uses for the process are product authentication, prevention of counterfeiting, and even biological barcoding, with people wanting to decipher the message needing to know the right nutrient and light needed to read the bacterial glow.
Each combination of 2 colors corresponds to either a letter, a number, or a symbol, and we array those in a particular order, and the bacteria do not glow unless they're exposed to a particular nutrient. And so when those bacteria grow in the proper medium, they develop the colors that they're designed to present, and the message, kind of like invisible ink, then appears magically.
Welcome to the Ig Nobel Prize ceremony.
The 21st annual Ig Nobel Awards took place at Harvard University this week, honouring scientists for research that makes people laugh and then makes them think. This year's prizes honoured work on why discus throwers get dizzy when hammer throwers don't, the use of wasabi to wake people up in an emergency, and our decision-making ability when needing to urinate. Mark Abrahams is in charge of the ceremony.
The point of them, in a way, is just to show people things that are so unexpected and entrancing, they are going to make you want to know more. Among the winners were the mayor of Vilnius, Lithuania, who won the Peace Prize for demonstrating a new way to discourage people from parking their cars in bicycle lanes. He runs over their cars with an armored tank.
The prizes themselves are presented by real Nobel Prize laureates and continue to grow in popularity each year.
And now, the Biology Prize. The Ig Nobel Prize in Biology this year goes to Darrell Gwynn of Canada and Australia and the USA, and David Rentz of Australia and the USA for discovering that a certain kind of beetle mates with a certain kind of Australian beer bottle. Please welcome Darrell Gwynn, David Rentz.
Mark Abrahams, the founder of the Ig Nobel Prizes, which were given out earlier this week, and he was ending that report by Mira Synthilingam. You can find the references for all of the news stories we've covered this week online at thenakedscientist.com/news.
From protons to photons and gluons to muons, The Naked Scientists. Science that's fundamentally more fun.
And this is The Naked Scientists with Chris Smith, with Dave Ansell and with Dominic Ford. We're solving all of your science questions for you this week, Dave.
If you want to get in touch, you can tweet at Naked Scientists, right on our Facebook page. That's at thenakedscientist.com/Facebook, or drop us an email. Our email address is chris@thenakedscientist.com.
I think because of the neutrino story we've had with neutrinos going faster than light from CERN, a couple of people have got in touch. Sharon Kopman is on our Facebook page, nakedscientist.com/Facebook will get you there. She says, neutrino, who's there? Knock, knock. Is this joke correct, or was Einstein wrong or right? Tristan Rosier Tucker says, what is a CERN physicist's favourite cocktail? Do you know, Dominic?
CERN physicist's favourite cocktail? Not
Dave?
sure at all.
I don't know, possibly something quite alcoholic.
Pina colada, allegedly. What is a nuclear physicist's favourite dinner? Either of you?
Don't want to think.
Dear, you really are a boring lot. Fish and chips, I'm told, according to this. Thank you, Tristan, for that eye-watering humour. If you can do better, do let us know. Roy is with us. Hello, Roy.
Yes, hi.
Far away.
Yes, I'm in the process of buying a company that supplies three products for power saving. One is a geyser blanket, one is a geyser timer switch, and one is a thing they call a power saver, which is a kind of capacitor thing, which I understand from my research on the net doesn't work, but there are lots of people around the world selling these things, which people say are a scam.
OK, so just to clarify, you put these things into your electrical supply, and in your case you're saying that you're making geysers or hot, in other words, hot water immersion heater sort of things, and they're supposed to cut down the amount of energy you're consuming in the home. Dave, what do you think?
There's a couple of ways of doing this. One of them is called power factor correction. This is if you've got very large motors, or sometimes very, very large electronic loads, you can draw current not at the same time as the voltage. So if you imagine alternating currents, the current voltage is going up and down and up and down. And if you attach it to a light bulb, then it will draw current at the same time as the voltage, and that's fine, and that's actually what the power company wants you to do. But sometimes if you have these strange loads, they can actually draw lots and lots of current when the voltage is very small and draw very little when the voltage is very high. That means that because your meter measures the total amount of current which is flowed times the time, and therefore you apparently are using far more energy than you actually are, so you get charged more than you should be, so it can reduce what you're being charged. It also drives the power companies up the wall because it causes havoc with all their systems.
Well, moreover, it means that they're doing less for their shareholders than they were before.
But yeah, I mean, despite the fact that this way you get more power, then that they're happier. But that's only a really big issue if you've got lots of big three-phase big motors, and that can, or possibly very large amounts of electronics. But I doubt that's a big issue with houses.
So Roy's immersion heaters are probably not going to benefit from having one of these things.
So not from that. The other way that some of them can work is by essentially just reducing the voltage. So it's basically like putting a variable transformer into your system. So whatever the voltage is coming in, it will always put out 220 volts. That means that your geysers will actually be less powerful, so you'll use less power, but that means you also get less heat. But
just going to use it for longer, aren't you?
But there are some kinds of lighting, especially fluorescent lighting, are more efficient that way, and things like some transformers are more efficient that way. So it will produce a big reduction in the amount of power you use, but you might get less out of it as well.
OK, a good answer. Thank you very much, Dave, and I hope that answers your question, Roy. We're doing quite well on the chemistry joke front. The boys out there, Ben and Tom, they need some help. They say, chemistry jokes, do you know any jokes about sodium? Nah. In other words, Na, right? Just for anyone who's not in the know, Na is a chemical symbol for sodium. Android Neox in Second Life says, a neutrino walks into a bar. The barman says, we don't serve neutrinos. The neutrino says, that's all right, I'm just passing through. Ba-boom. Right, OK, on the phone, we've also got Michael, who's got a question for us. Hello, Michael.
Hi there, hello.
Tell us about yourself. Where are you from?
I'm from Poland. It's the northern part of Poland.
Terrific. Which bit? Near Gdansk, where they make the boats?
Gdansk, yeah.
On the Baltics. Nice there. I've been to Gdynia. It's very nice up there. And you listen to The Naked Scientists in Poland?
Yeah, I'm listening to it, and I love the show. Keep up the good work.
Oh, terrific. You can come again. What would you like to know?
Yeah, I've got a space question for you. So, as far as I know, our solar system has got pretty big asteroid belt. Is it possible to bring some of those asteroids close together enough that their combined gravitational pull would start gathering smaller asteroids and, in final effect, form a planet in the place of the asteroid belt? If yes, how big would it be, and what effect would it have on our solar system?
Well, this is one of those really good questions where I have to say we don't completely understand the answer. The way that we think planets formed in our solar system and elsewhere is by solid particles of grit-like material, which has come together, and that has then formed into small asteroids, or, well, first of all pebbles and then into asteroids, and then those asteroids gravitationally attract one another, and they come together to form large masses that turn into planets. Now, for some reason, we have this gap in the middle of our solar system between Mars and Jupiter, and it's a big gap in which there are no planets, but there are lots of these small asteroids. So given that no planet has formed in the last 5 billion years since the solar system formed, we can probably say there is some good reason why a planet has not formed there. And probably the reason is that those asteroids are too close to Jupiter, and Jupiter is stirring up the orbits of those asteroids and stopping them from gravitationally attracting to one another and coming close enough together to form together into a planet in that gap between Mars and Jupiter.
There was a terrific paper, it was in Science, about 2 years ago by a guy called David Minton, who is, I think, in Arizona, and he did a mathematical model, another computer model, of the Kirkwood gaps in the asteroid belt.
Yes.
And there are all these holes in the asteroid belt which can, in some cases, can't be accounted for. And they worked out where Jupiter had come from and where it had gone to, because it didn't always end up in the same position it's in now. It's migrated in a bit during its evolution of the solar system. And this has created, when they put it into their model, what they dubbed gravitational resonances. So when it lined up with all the other planets in the right sort of place, it shook the asteroid belt a bit and dislodged some of these other bodies from the asteroid belt, kicking them onto Earth-bound orbits, actually, and probably accounted for the late heavy bombardment that rained in on the planet 3.9 billion years ago. But their point was that the gravitational tug there is so unpredictable and so intense that it actually stopped all these things accumulating and accreting into a planet, or even if they did at one time, they fell apart again.
Yes, that's absolutely right. The Kirkwood gaps are really the forensic evidence that Jupiter is the problem and why no planet has formed there, because the Kirkwood gaps are lined up with places in the asteroid belt where you would be orbiting twice as fast as Jupiter, or perhaps 1.5 times as fast as Jupiter. And for some reason, there were no asteroids there, and that suggests that there is some reason why you can't be in orbit at that point.
Dominic, thank you very much, and thank you for a terrific question. Michael, if you would like to ask us a question here on The Naked Scientists, or better still, you have a physics joke for us, Sean McCandles is waiting to come on. I hope, Sean, you're primed with an appropriate neutrino-inspired joke for us. Get in touch. chris@thenakedscientist.com is the email address. You can also tweet @nakedscientist, or we've got a Facebook page running. It's thenakedscientist.com/Facebook. And here with another question for Dave, I think this one, I hope it's for Dave, looks tricky, is Sean. Hello, Sean.
Hi, how you doing?
Very well, thank you. Tell us about you. Where are you?
I'm in New Hampshire, in America.
Oh, I think you're probably the first person from New Hampshire we've had on here, so that's really good to hear from you. Listen to the podcast.
I do.
Excellent. What would you like to know?
Yeah, I was on a business trip recently and experienced the earthquake, the 5.8 in Washington, D.C. My question is how do earthquakes occur that are nowhere near a plate boundary?
Because, of course, Dave, Washington, D.C. is not on a plate boundary, but did have this fairly substantial shake-up.
Yeah, it's nowhere near a plate boundary. There's a variety of things, and basically anything which can apply large forces to the plates can cause earthquakes. You can get earthquakes a long way away from plate boundaries, actually still associated with them. So in India, where you're creating the Himalayas and you've got a huge amount of compression, you can still get earthquakes hundreds of miles away from that plate boundary just because the compression and the crushing there is so immense. You still get great big earthquakes a long way away from the edge. You can also get earthquakes when people build big reservoirs. So you put a load of water on the ground, that essentially loads it. So the comfortable place where the ground wants to be is a bit lower. So the only way it can move there is if it's not kind of squidgy like clay, is by cracking. And so you get small earthquakes like that. You can get earthquakes as ice melts. We're still getting earthquakes in Norway, and actually most of the earthquakes in Britain are probably associated with all the ice melting after the last ice age. That unloading the north end of Britain and Norway. The ground is rising slowly, actually, a few centimetres a year, especially in Norway, and that eventually builds up some pressures and stresses in some places until it breaks. I think the one thing I've vaguely heard about the Washington one, they don't quote me on it, is that could also be sediment building up at the edge of the continent, building up on the ground. That's pushing down, and eventually that could build up enough to produce an earthquake.
So even though you're not near a plate boundary, you can still have an earthquake nonetheless. Thank you for the question, Sean. Dave Marchant has asked us, how does a baby acquire immunity via the mother's milk? Are the mother's antibodies absorbed through the gut? The answer, Dave, is yes. In a very early baby, the gut is quite porous, and it's specially set up so that when antibodies, especially in the milk that mother produces first, and this is called colostrum and is very antibody rich, those antibodies go down into the baby's intestine, and there are special receptors there that pull the antibodies across the intestine and put them into the baby's bloodstream. Unfortunately, this is the same mechanism that gets exploited to get some viruses across the young baby's intestine, including HIV. The risk of a baby catching HIV from a mother, if it's born via the normal route at term, is actually quite low, but if the mother breastfeeds the baby, then the risk can go up quite significantly. So not breastfeeding in those circumstances can actually spare quite a lot of infections with HIV because the virus gets pulled across that rather leaky baby's gut. Of course, the major way that antibodies get into a young baby are via the mother's placenta. Because once a baby goes beyond about 28 or 29 weeks of gestation, the placenta turns on special receptors called FC receptors, which grab from the mother's bloodstream antibodies of a class called IgG, and they put them into the baby's bloodstream, and that way when the baby comes out, it's what's called passively protected. In other words, it's got antibodies recognising all the things that its mum is normally being exposed to in the environment in which she lives, so it's a good way of protecting the baby for its first few weeks of life, because those antibodies circulate for up to 6 months, actually, while it makes its own immune response and builds its own immune system. Righto, now let's turn to planet Earth, because scientists in the UK are heading off on one of the most ambitious polar exploration programmes that's ever been undertaken. Subglacial Lake Ellsworth involves drilling down through more than 3 kilometres of ice into a hidden Antarctic lake to look for life. Drilling is due to start in the Antarctic summer of 2012 to 2013, and Planet Earth podcast presenter Richard Hollingham has been to see the equipment in action. Sadly for him, it's not in the Antarctic yet, but it's on a farm near Cambridge. And he spoke to programme manager Chris Hill and, firstly, the principal investigator for the study, Martin Siegert, from the University of Edinburgh.
Lake Ellsworth is at the bottom of the West Antarctic ice sheet. It's underneath about 3 kilometres of ice. The lake is roughly 10 kilometres long, 2 or 3 kilometres wide, and the water depth of it is about 150 metres. So it's like a rather large Scottish loch underneath the ice of West Antarctica.
Why is it water?
Very simple. The background geothermal heating is all you really need to get the ice temperature to be at the pressure melting point beneath about 3 kilometres.
So that's heat from the rock?
Yeah, it's not unusual geothermal heating. It's just background levels of geothermal heat that you get everywhere on the planet, and that's sufficient to warm the ice to the level that it will melt. And it's expected in Antarctica. We know of about 400 subglacial lakes that are located in various parts of Antarctica. Lake Ellsworth is the one that we're investigating in the next few years.
Why is it so interesting?
Well, there's a number of things that we want to understand about subglacial lakes. It's been 15 years since a breakthrough paper highlighted the scientific interest in subglacial lakes being a place where life might exist, unusual microbes in a very extreme environment, and we're interested in understanding how life can survive in these places, what life exists in these places, whether it's thriving, whether it's on the edge of extinction or what have you. And the sediments on the floors of subglacial lakes may give us very important information about past climate change and ice sheet change in Antarctica.
So what are you planning to do?
Well, our plan is to access and sample the lake water and get samples of the sediment as well. And to do that, it's rather difficult because we have to get all the way through that 3 kilometres of ice in a very clean way without disturbing the lake unduly, and getting those samples back to the surface where they can be treated and analysed in laboratories.
Because there might be life there. You don't want to contaminate it, and you want to ensure that if you find traces of it, it's from the lake and not something you put in there.
Absolutely right. The science demands that we do things cleanly as well. We're very likely to be encountering very low concentrations of microbes and chemicals that we want to measure. And unless we keep the experiment really clean, all we'll do is measure the things we take down with us.
Now, Chris, it's your responsibility to make sure this happens.
That's right.
When we talk about drilling down, you're actually using hot water to drill.
That's correct. Traditional drilling techniques would have used some sort of drill corer, but that takes a long time. And hot water drilling is actually the cleanest, quickest and most efficient way of accessing the lake.
So what have we got here? I mean, these really are big paddling pools. 2 of them set up at the moment. So they're full of water, and I think it's quite a nice sound when you tap the side. These are the pools that you have hot water in to drill down.
Kind of. What we need in order to undertake hot water drilling is a huge amount of water. And, of course, there's loads of water in Antarctica. The problem is it's all solid. So the very first thing we need to do is to get together a large amount of snow in one place and start to melt it. And that's what these pools are for, is to melt some 90,000 litres of water to prime the drilling system to start drilling. Once we are drilling, there's no problem, because as we're drilling down to the lake, we're generating lots of melted snow as we go, which we can recirculate.
It's really a jet of water at the end of these giant hose reels, which you've got trailing across the field here.
In simple terms, the system is really straightforward. We take this melted snow on the surface, and the first thing we do is filter it. Then the next thing we do is heat it through a very clean boiler system up to approximately 97 degrees Celsius. We then run it through a bank of high-pressure pumps, and we then basically push this water through a very long hose, about 3.4 kilometre hose, which has a jet nozzle on the end, which just allows us to melt through the ice at an incredibly fast rate.
Martin, you've got your hole. What do you then do?
We have 2 items that we'll send down. One is a probe which has sample chambers on it, and that will be lowered down the water column, taking measurements as it does so. It will scrape the sediments on the floor of the lake, and then it will take samples as it comes up, and we'll take that back to the surface and bring them back to the laboratories. The next thing we'll do is we'll put a coring device in, which can take a 3-metre core of the sediments on the floor of the subglacial lake and transport it back to the laboratories.
It sounds to me almost like a space mission.
There's also another analogy to space science, that the experiment that we conduct in Lake Ellsworth at some stage in the future may well be done in Europa, which is an ice-covered moon of Jupiter with an ocean underneath it. And people speculate that there may be life on Europa. Well, to test that hypothesis, is there life on Europa, will require more or less the experiment that we're going to do in Antarctica. It may be 20, 30, 50 years away, but we're very keen in Lake Ellsworth to make sure that we're documenting everything that we do, so that at some stage in the future, if people want to learn how we did this experiment, it will be available to them.
It's getting very exciting down in Antarctica, because, of course, Lake Vostok, which is another one of these massive lakes, is within a gnat's whisker of being opened up for the first time in a very long time, and no one knows what's in there. Anyway, that was Martin Siegert, and he was with Chris Hill. They're from the subglacial Lake Ellsworth project, and they were speaking with Planet Earth podcast presenter Richard Hollingham.
And you can find out more Planet Earth resources online at thenakedscientist.com/planetearth.
Now, very exciting kitchen science experiment coming up very shortly. Dave and Ben are outside and in position, and if you want to have a go at this, you need to grab yourself a 9-volt battery and some wire wool. They're going to be starting an inferno, they tell me. If you'd like to get a question in for The Naked Scientists, it's Chris Smith, Dave Ansell and Dominic Ford here answering all your science questions. Email chris@thenakedscientist.com or go to our Facebook page, nakedscientist.com/Facebook.
Lifting the lab coat on the world's best science. The Naked Scientists.
It's The Naked Scientists with Chris Smith, with Dave Ansell and Dominic Ford. It's getting dark outside, so I should have no trouble seeing what they're promising is going to be quite a big inferno for this week's Kitchen Science. We've sent Dave outside with Ben Valsler and a very dodgy-sounding experiment to set some iron alight. Ben?
I wouldn't say a big inferno, but certainly a fire of sorts is what we expect to see out here. Dave, you're going to be setting light to something that I wouldn't traditionally think of as something that burns. Now, let me get this right. You're going to burn some iron.
Yes, that is absolutely correct. I'm going to set fire to some iron. Now, iron burns very, very hot, so we've come outside away from anything flammable, so as a BBC thing to calm down. And I've also got some scales here. So I've got some wire wool, some stuff you might use for scouring pans. It's basically lots of very, very fine wires of iron. And I have a 9-volt battery.
Now, when I think of iron getting hot, I think of it as glowing and melting, but I don't necessarily think of it as burning. Is there something strange about that? Do all things ultimately burn?
Not everything oxidises, but iron certainly does. It oxidises very slowly, normally at room temperature with a bit of water, and it turns into rust. But all we're going to do is speed that process up a lot, partly by heating it up, by touching the battery to it, passing a very large current through it so it gets very, very hot. And the other way that we're speeding it up is that this is a wire, incredibly fine wire, so lots of oxygen can get it at once, so it should speed up the reaction.
So the fact that we're using wire wool or iron wool is actually very key to making this work.
Yes, it would work, but we might be sitting here for 6 months with normal bits of iron.
And we're using a battery. Now, this is one of those sort of cuboid batteries. They're called PP3 batteries, I believe. 9-volt batteries. Quite a lot of power in one of those. Could we actually just get this lit just using a lighter or using a small fire that we already had?
You can do it with a blowtorch. I think with a lighter you won't really get it hot enough. It probably would work with other batteries, but you might need to get the contacts very close together. And so 9-volt battery is very convenient because the contacts are exactly in the right place.
So the advantage really is that those contacts are on the top. Now, you're actually putting this onto a weighing scale. Now, I'd have thought we'd want to just put it on something fireproof. What's the significance of weighing the burning iron?
Well, normally when you burn something, it disappears, so it gets lighter, so I thought we'd compare that with this. So now I'm going to touch the battery to the wire wool.
Okay, and just, it instantly ignites. And then these tiny little sparks just seem to crawl through it. Now, it started off at about 20-ish grams, and it's actually now about 20.5, so, well, just under 20.5, so it's smouldering away. It's definitely burning, not melting, but it seems to have gained weight. But it looks to me like some of it's burned away. How does that work?
Well, instead of turning into a gas when carbon reacts, so when carbon or charcoal reacts with oxygen, it turns into carbon dioxide with gas and disappears. If you burn iron, it turns into iron oxide, which is a solid, and it's gained oxygen, so it's heavier than it used to be. So when you burn a metal like iron, it gets heavier rather than lighter.
But it doesn't look like rust, and rust is also iron oxide.
There's two different iron oxides. There's iron FeO and Fe2O3. Normal rust is Fe2O3 with a little bit of extra oxygen, and it's orange. FeO is a different kind of oxide, and it's kind of a bluish tinge. And that's what we're making here because it's reacting very quickly and there's not quite enough oxygen to produce Fe2O3.
Well, it's still burning away, and it's definitely quite warm. Does this also tell you, as well as being an interesting experiment in the chemistry of iron, that you should really store your batteries carefully?
Yes, nowhere near wire wool, and definitely leave this for a long time to cool down because it could be quite dangerous if you touch it. At the moment that's at probably 600 or 700 degrees centigrade, so leave it somewhere very safe. Don't assume that it's gone out when it looks like it's gone out, so leave it a good time somewhere fireproof to recover.
So yet another safe and fantastic kitchen science that you can try it at home, setting fire to some iron using a battery.
Thank you, Ben and Dave. It was amazing. I was watching through the window and literally one touch from the battery and whoof, off it went. 600 degrees, get that. Dave's written it up on the internet. If you'd like to find out more about how to do that experiment safely and what it looks like, nakedscientists.com/kitchen science. There is a wonderful video there showing it all in action. OK, what a terrific question. I have had this happen to me, Dave, so I'm looking forward to the answer. Tony Bunn says, when heating soup in a soup bowl in a microwave oven, the soup begins to heat rapidly on the perimeter of the bowl and remains lukewarm in the centre. Why?
OK, this might be something to do with a slight misconception of how microwaves cook. People often say they cook from the inside out. They don't strictly. What they actually are, microwaves are a form of electromagnetic radiation, a form of light, and they're absorbed on the outside. They're absorbed within the outside inch and a half or so of the food. So right in the centre, it's kind of insulated from the microwaves by all the other food around it. So the soup in the middle is going to be getting less heating than the soup on the outsides. Also, the soup on the outsides is thinner, so it's going to be heated from all directions. So the soup on the outside is essentially getting more microwaves than the soup in the middle, so it gets hotter.
Thank you, Dave. And what can I do to remedy the problem so that my soup is more evenly heated in future?
Take it out occasionally, give it a mix is your best bet.
I'll remember that. Dominic.
Now, we've got a question here from Chris Martin, which I think might be for you. Would swimming from a submarine cause the bends?
Yeah, good question. One I've actually pondered on myself, which is why I guess it's gone my way. The answer is probably not. Now, the reason for this, actually, is that when you're in a submarine, the air that you're breathing in the submarine is not under pressure, or at least not under demonstrably higher pressure than ambient pressure, i.e. surface pressure, because the submarine can be thought of as an incompressible tin can underwater. So although the water is pushing in very hard on the submarine, the air inside is not feeling any extra pressure when the submarine goes down to the bottom of the ocean. Therefore, you're breathing air as though you were breathing at the surface. And that means if you escape from the submarine, say you went out of one of the torpedo tubes or something in a submarine that was stuck underwater, then although you would immediately be exposed to extremely high pressure, depending on how deep the submarine was, it would be more or less accordingly, then what would be pressed in on you would be the surrounding water pressure, and it would be subjecting the air already in you to that higher pressure. And this means that the air would dissolve more in your blood, including the nitrogen that was in your lungs at the time, but there wouldn't be very much of it. And as you went up to the surface, you would find that nitrogen coming back out of solution and back into your lungs and back into your blood. But again, there would only be a very small amount of it. If you were a scuba diver, on the other hand, you would have a problem. And what happens there is that scuba divers go down to the bottom of the ocean, say 40, 50 metres underwater, and they're breathing compressed gas. In order to inflate the diver's lungs, to compete with the surrounding ambient pressure underwater, you've got to deliver the gas at higher pressure than the surrounding water. Therefore, you're breathing gas which, the deeper you go, becomes increasingly dense and increasingly high pressure the lower you go, and therefore more is going to dissolve in the bloodstream the lower down you go of the oxygen, but also the nitrogen is going to be forced into solution. Nitrogen's not very soluble. And then when you come back up again, because you have a body load which has a lot of dissolved gas in it, as the pressure comes off, that nitrogen comes back out of solution and it forms bubbles in the tissue, and you get the bends. If you are not breathing compressed gas, this won't happen. Whales don't get the bends, or at least not often, unless they resurface incredibly rapidly. And we made a very nice video of this. If you look at Naked Scientist Scrapbook on YouTube, you can actually see the footage we did recently, and it's why don't whales get the bends but divers do, and it goes through basically the physiology of this.
So the problem with the divers is that they're breathing air compressed for a very, very long time, whereas if you escape from a submarine, it's only a couple of lungfuls at the most, so there's not enough time for it to dissolve.
Well, exactly. You're breathing air which is under pressure, so it's pushing a lot more nitrogen to dissolve, and nitrogen doesn't like dissolving. It's very insoluble. You also can't metabolise it, so even if it's in a tissue somewhere, it won't get used up. So you're increasing your total body load of nitrogen because you're breathing compressed gas, and the longer you spend underwater, the higher the burden of nitrogen in your body. As you go back to the surface, the pressure on you comes off, and that pressure was keeping the nitrogen dissolved. It's now gone, so the nitrogen comes back out of solution and turns into bubbles again.
But I guess if you're escaping from a submarine, at some point you're going to have to take a breath full of compressed air, otherwise you're going to get flattened when you get out under high pressure, so you come out through some kind of airlock or something, so you'll be breathing compressed air for a bit.
That's true. As the, say, torpedo tube floods, it's going to compress the air in there. and that will, in effect, subject you to compressed air. If you don't breathe it, then what I say stands. If you do breathe it, you would have a little bit more nitrogen in your body, but assuming you did it only for a very short time, I don't think it would make very much difference, really. Now, Dominic, I've had a roasting at the hands of Dave. Now it's your turn, not at the hands of Dave, at my hands, and the hands of Stephen Fleming, who says on Facebook, nakedscientist.com/Facebook, at the winter solstice, why does the sunrise get later for several days, the mornings get darker, whilst in the evenings, sunset gets later? Why aren't they in sync?
That's a really tricky question, and what it comes down to is how we define the length of a 24-hour day. Now, the traditional way that you would do that is you would look at the sky and you would look at when the sun is highest in the sky, and you would call that noon, the middle of the day. And then the next day you would go out and you'd look at when the sun was highest, and that would be the next noon. Now, the other way that you can define the length of a day is to have an atomic clock, which is measuring the progress of the laws of physics, and is giving you a very precise packet of time of a fixed length. Now, it turns out those two definitions of the length of day are not exactly the same. The length of time it takes for the sun to come round from one noon to the next varies over the course of the year. And the reason is because that period is not just the time it takes for the Earth to rotate on its axis, but also the time it takes for the Earth to catch up with the fact that the sun has moved a little way across the sky. And the way in which the sun moves across the sky changes at different times of year, because, for example, the Earth's orbit is elliptical, and so the Earth is moving at different speeds at different times of year.
I did hear one person put this as a bit like slipping a gear, because because you've got an ellipse, not a circle. As the sun goes along the flat side of each ellipse, it's got to sort of slip a gear a bit. The Earth has got to slip some gears as it turns in order to make it work, if you see what I mean. It's not just a straightforward circle. That's not a bad way of thinking about it. Now, what that means is that noon doesn't always happen at exactly 12 o'clock on every day of the year. For example, I think now at the beginning of October, noon is happening about 10 minutes before 12 o'clock by your watch, and it's getting earlier, and in a couple of weeks' time it will be at quarter to noon, and then it will turn around and it will start getting later as the durations between noons get longer in December towards the winter solstice. So what's happening at the winter solstice is that sunset turns round in the middle of December, but sunrise turns round about a week later because the solar day, the time between noons, is drifting through the mean day that we call civil time.
So the length of day is changing and the time of noon is changing, so the two add up to this effect.
Yeah, that's exactly right.
Well, I'm glad you could agree on that, because just for the sake of people who are listening to this at home, they had an argument for about half an hour trying to get that right, so I'm very pleased. And there you go, that testimony to the fact that we fact-check everything to death at The Naked Scientist. Thank you very much, Dominic and Dave, for answering. That's a very hard question to answer and answer well. I think you did very well, so thank you very much.
Bringing the facts to bear. The Naked Scientists.
It's The Naked Scientists for Chris Smith, Dave Ansell and Dominic Ford. Dominic, can you answer this one really, really quick, just because it's just a sort of aside related to the asteroid question you answered earlier? Nat Spirit in Second Life, he says, do other solar systems have asteroid belts too?
It's really too early to say. We've seen planets around several hundred, actually, other stars in the last 15 years or so, but the mass of the asteroid belt is quite small. I don't think we really have the sensitivity to detect something that's small and which is that spread out across the solar system. You really need a big concentrated planet which is having a gravitational influence on its host star. Chris, we've got a question which I think is for you here from Michelle. The autumn colours looking good outside, but what causes leaves to change colour in the autumn?
Yes, terrific point. The answer to this is that leaves look green because they contain the pigment chlorophyll, which is what they need to do photosynthesis, the process of grabbing energy that's in sunlight and driving a chemical reaction with it in order to turn carbon dioxide and plus water into glucose, C6H12O6. That's what photosynthesis is. But leaves also contain other chemicals, including antioxidant chemicals. And one of the chemicals they contain is a family of chemicals called carotenoids, which, as the name suggests, are orangey or yellow. So once the chlorophyll goes away in the leaf, then you see that orangey-yellow colour. And as we get towards autumn, because the leaves know that they're senescing, they're getting old, they're going to be lost soon, they reduce their rate of chlorophyll production, and that means that there's less of the green pigment in the leaf, and therefore the yellow colour that the green was previously hiding is disclosed, and that's why the leaves appear to change colour, because the leaves are running out of chlorophyll. Some leaves also turn a red colour, though, don't they, which is nice. Not all leaves, but some species, and that's because actually they make another class of chemicals called anthocyanins. These are the same things you find in beetroot. They're a dark, deep red colour, and they're also a family of antioxidants. And what the plants do is to put those into the leaves to sustain and support and prevent stress in the leaves as they go towards winter. And that means the plant has longer to scavenge back from the leaf the things that it wants to rescue back into the plant before it dumps the leaf, because once you lose the leaf, you're losing tissue, you're losing salts and chemicals and potentially other good-for-you things. So by protecting the leaf with these other anthocyanin molecules for a little bit longer, you hang on to your leaves for slightly longer than you otherwise would. Now, Dominic, I'm going to bounce this straight back at you, sticking with the space theme. I love this one. A lot of debate on the forum on this. Kurt Larson says, would a siphon work in space? In other words, if you had a siphon on the International Space Station, as you would do on Earth, would it work? No, it isn't. No, it wouldn't, because you need gravity to make that siphon work. If you imagine the fluid, at different points along the length of that siphon, at some points the siphon will be going uphill, and at other points it will go downhill, and there will be a gravitational force on the fluid inside your siphon. And where the siphon is going uphill, the force is pulling the fluid backwards along the pipe. And where it's going downhill, that force is pulling the fluid forwards along the pipe. And what you need is more bits of length of your siphon going downhill with those forward forces than you have going uphill. And that means that because of the water pressure inside that siphon, the places where the force is going downhill is dragging the fluid along the whole siphon from the beginning to the end. On the International Space Station, you have no gravitational force, so there'll be nothing to drive the fluid along the siphon. Therefore, it just wouldn't work. Thank you. A very quick joke before we go to John's question for Dave. Flair Rhymes Saho on Twitter says, f of x, that's a mathematical function, walks into a restaurant, manager says, sorry sir, we don't cater for functions. I like that one. That's pretty good, actually. It's better than the bloomin' sodium one they had earlier. Dave, John's got a question for you. Hello, John.
Hello.
Fire away.
Here in the States, we have a liquid product called Rain-X. When you spread it on your windshield, then raindrops beat up. Rain-X seems to add an invisible waxy surface to the windshield. If the only light source is directly in front of you, as with normal rural night driving, all of the water droplets vanish almost magically. If you drive under a street lamp when the light comes from the side, then you can see the water droplets, but just for a second until the light passes. I assume that Rain-X works by forcing the raindrops to be tiny hemispherical lenses, but I'm not sure about the details. Does it use refraction or total internal reflection or both?
Dave.
Okay, the first thing it's doing, it's covering your windscreen with something called a fluorosilane. It's basically a silicon oxygen with fluorines on the side, which is incredibly hydrophobic. So the water droplets, instead of forming kind of flattish lenses, they form very, very circular things. I think what's going on is they're much, much stronger lenses. So they bring any lights to a focus very, very close to them, and then the light spreads out and is evened out all over everywhere. So instead of you seeing a really bright light, you see a kind of a much, much dimmer light, and you hardly see them at all. And then probably when the light comes very close to you, something more complicated happens, and you get the bright lens.
Dave, thank you very much. We're talking of hard questions, and you did very well to answer that so quickly. With our question of the week, here is Diana O'Carroll, who is breathing for two.
This week, take a deep breath.
Hi, I'm Felicity, and I'm a medical student from Peninsula Medical School. I know that during pregnancy, a fetus gets oxygen from its mother via the umbilical cord. So I was wondering, do pregnant women have to breathe more, or do they just use oxygen more efficiently?
So if you've got more bodies to fill with oxygen, you'd need to breathe more of it in.
Good afternoon. I'm Jerry Hackett. I'm a consultant obstetrician and gynaecologist who work at the Rosie. Amongst many other things, I'm a fetal medicine specialist, and you've kindly asked me a question about pregnant mums and do they have to breathe more? Certainly during pregnancy, a mother and her baby need more oxygen. Actually, many people think that the oxygen is just for the baby, but actually at least half the extra oxygen the mother is taking in is for the placenta. Certainly also during pregnancy, the mother's basic metabolism just gets higher. During pregnancy, mothers do breathe more. They, in fact, breathe more deeply. They don't breathe more often, more frequently, just more deeply. And actually, strangely enough, despite taking up extra oxygen in her blood, mothers in pregnancy often feel breathless. And that's one of the most common symptoms of pregnancy is breathlessness, strangely enough. So during pregnancy, mothers will feel more breathless, even though they're taking up more oxygen and letting out more carbon dioxide. They do this in part by movement of the diaphragm. Of course, as the pregnancy gets larger, you'd expect there to be less movement in the diaphragm, but in fact there's just as much as always, and so that tidal volume, the amount of air that a mother will breathe in and breathe out, is much the same in pregnancy as outside of pregnancy. The airflow is much the same. The extra oxygen passes through the placenta, it's taken up by the placenta, but also by the baby, and it transfers quickly over to the baby's side because the hemoglobin, that is the red cells actually in the baby's circulation, picks up oxygen much more easily than our own hemoglobin would do. It binds that oxygen and then releases it into the baby's circulation.
Pregnant women don't breathe more often, but they do breathe more deeply, and surprisingly, the movement their diaphragm can make isn't impeded by the growing baby. And on the forum, Clifford Kay said that adding £50 to anybody will make it take more energy to walk across the room, and oxygen is required to release that energy. Next week, can energy be released from poo?
Hello, I'm Matthew from Cambridge. After breakfast this morning, I was wondering if human excrement can be used to produce electricity. It seems like a great source of energy, and the infrastructure to collect it is certainly in place. Is this possible?
So can we make the currents in our post-breakfast deposits into alternating current? Answers to Chris at thenakedscientist.com. You can write on the forum at thenakedscientist.com/forum. You can Facebook us or Twitter at Naked Scientists.
Diana O'Carroll. So get in touch if you know how to turn waste into a miracle source of electricity. That's it for this week. Thank you to our production team, Tom Simpkins, Ben Vousler, Mira Sinthalingam and Emma Stoy. And thank you for your science questions. Next week, we're exploring the alternatives to petrol. We're meeting the scientists who are using algae to make biodiesel and turning rubbish into hydrogen. Do join us if you can.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at thenakedscientists.com.